Good afternoon. I'm intending on covering CPU scheduling for the second time. The recording on Friday failed to materialize. So we're having a look at scheduling algorithms and criterion for choosing a given algorithm. And the keywords that we're focusing on is context switch, preemption, FIFO queues. Right? So a little bit of background. There are at least five well-known criterion for selecting a scheduling algorithm. And it might not have crossed your mind that the way in which the next thread or processor or program is scheduled is going to make a significant difference to the behavior of the processor system. And some of the work that we're going to do now is related to the work that we did right at the beginning of the course, where we looked at the scheduling algorithms for lifts and the read-write arms of uh, a disk head. So it's related, but in many respects it's quite different. So we're going to focus on waiting time in particular, and we could have we could have well, going through this list of five factors, we could have first of all looked at optimization of CPU utilizing, but we're not going to do that. What we're going to do is look at waiting time and very briefly mention three other algorithms that might affect the performance of a CPU-based system. So definition of waiting time is this. A scheduling algorithm doesn't actually affect the amount of time which a process takes to complete or perform its I/O, of course, because I mean, if a man takes 100 seconds to run 100 meters, you're not going to actually change that fact. But depending on the way in which you allow 10 men to start running 100 meters, might affect the overall time it's going to take those 10 men to complete the 100-meter course. So waiting time affects the amount of time that a process or thread spends waiting on the ready queue prior to periods of execution on the processor. Well, what's the ready queue? Just to remind you from weeks and weeks and weeks ago, it's just a queue of processors all waiting in turn to run on the CPU. Because logically, at most, you can actually have exactly one program or process or thread running on a processor unit. You can't execute two processors literally in parallel on a single piece of hardware. So waiting time or wait time is the sum of the periods spent waiting in the ready queue. In other words, the total time um, that all the processors will need to wait before they're executed. And we're interested in average wait time, the average waiting time for a given set of processors. And the big question is there anything that we can do to reduce the average waiting time? Because if you think about it carefully, then if you do manage to reduce the average waiting time, it's going to benefit all the processors. I mean, rather than have to wait an hour to do an important job, I can actually make a start earlier if I can find a mechanism for reducing the average waiting time. So other factors that we might be interested in, apart from wait time, is the, the throughput, the rate at which you can actually get n processes to complete. Are there ways in which you can alter the throughput? Is a mechanism for altering or improving the turnaround time of a particular process? Well, um, it doesn't take a lot of thought to see that it's possible. Um, are there any ways in which you can alter the response time of a particular program? And what I have in mind here really is simply a system such as an engine management system that's actually monitoring 50 different external events. In other words, it's connected to 50 sensors, and one of the sensors might be measuring the air pressure in each of its car's four tires. Another sensor might be attached to a device that's actually measuring the petrol air mix in order to optimize the power yield of the car's engine and so on. Anyway, that's all a bit by the by at the moment. They're all quite interesting subtopics, but we're interested in wait time and algorithms that relate to uh, ways of affecting the average wait time. So the first that we're going to consider is FCFS, which people from term one will actually recognize as simply standing for the first come, first served. It's the simplest algorithm and it's easily implemented using a straightforward FIFO queue, first in, first out. Some data structure that when you enter an object onto it, in or into it, and you need an object that's being queued or being stored in that data structure, you will actually end up picking the one that's waited the longest, first in, first out. Okay, as opposed to last in, first out, and that's very much um, the discipline yielded by a stack. If you remember, if you put a plate onto a stack of plates, and a short time afterwards you need a plate, you'll remove a plate, but it was actually the last thing you put onto the stack. You remove it. It's going to be the first out. So the average wait time can be lengthy. If you consider the following three threads or programs or processes, P1, P2, P3, P1 has a burst time of 24 milliseconds. P2 has a burst time of 3 units of time. P3 has a unit of 3 milliseconds or other units of time. The question is, well, what on earth does Kindberg mean by burst times? It's just an estimated length of time needed for a program or a thread or a process to complete its operation. So P1 having a burst time of 24 simply means it needs 24 units of time on the CPU for it to run to completion. Okay, so little statement of what burst time is, and I've actually qualified it by time needed on a CPU before um, it needs to do input or output, or it actually completes operation. Well, the fact of the matter is that a program, something like 99% of all programs need to perform input or output. And to do input or output, you don't actually need a CPU. You need some kind of dedicated device. For example, I mean, a running program might need some audio input, in which case the program actually stops running and all attention is switched to a microphone. And after your message has been entered, the program will start running again. Okay, so that's something for you to think about. So with first come, first served, P1 was the first to come, so it's got a wait time of 0. Look, I've got a 0 here. P2 has had to wait 24 units of time. Why? Because P1 has a burst time of 24. So it's only after 24 units of time that P1 will finish, allowing P2, which was the second process to arrive, to start. It's got a burst time of 3. So At time t equals 27, i.e. 24 plus 3, P3 will actually have the opportunity of running. That's at time t equals 27. It finishes at time t equals 30. So it's easy to calculate the average wait time for those three processors, given that each has these specified actual waiting times. And the average waiting time is 0 plus 24 plus 27, all divided by 3, which gives you 17. But what if the order of arrival of those three processors onto a ready queue, a queue of processors that are ready to run but aren't actually running? So supposing the order had been P2, P3, then P1, the average wait time would have been 3 milliseconds. Why? Why? Well, if P2 is the first, it's got a burst time of 3. Then at time t equals 3, P2 can run. It's had to wait 3 units of time. P2 hasn't had to wait at all. And then P3 will actually have to wait for a further 3 units of time. In other words, the wait time for P1 is 6. So 6 plus 3 divided by 3 is 3. Right? So you've radically altered the average wait time just by thinking of altering the order in which they arrive. And what we can see straight away is that the average wait time is actually a function of the variation of the burst times of all the constituent processors. And I've made a note here about something called the convoy effect, and Google what a convoy effect is in the context of CPU scheduling. Right. So, okay, let's move on a little bit. Now, first come, first served algorithm, as it stands, is not preemptive. In other words, it's just saying, whatever you process arrives uh, in a particular order, execute it. And a process won't be kicked off the CPU as a result of um, burst times. So this takes into account burst times and um, shortest job first, SJF, shortest job first scheduling. Association of the length of the processor's next CPU burst time with a given process. So in other words, when a processor is available, in other words, it's not running a program or a process or a thread, the process with the shortest next CPU burst time will run. And if there's a time, you can always resort to first come, first served. Whichever was in the queue first, well, and they both have the same burst times, choose the first to arrive. So um, consider if I can move uh, the page back again. Sorry about that. Just waiting to get back to my original position. So we're looking at the shortest remaining burst time first scheduling. SRFS, shortest remaining time first. You pick to pick a process to run next. You choose the one with the shortest remaining, not the shortest absolute burst time, but the remaining burst time. So look at this and think about this very carefully. Here's my illustrative example. Consider 4 processors, P1 to P4, which arrive in that order. And they have burst times of 8, 4, 9, 5, respectively. So preemptive preemptive shortest job first will result in the following schedule. P1, why P1? P1's got a burst time of 8. That's not the shortest burst time, is it? Well, we can, because we're looking at preemptive shortest job first, we can actually start running uh, P1, which has a burst time of 8, and we're running it for exactly 1 unit of time. And then P2 comes along, joins the queue. It has a burst time of 4. So what we're going to do is to take off P1, take P1 off the CPU. So P1 still has 7, it's still got a next burst time of 7. 7 compared with 4 uh, means that P2 will run next. And it's actually going to run for the next 4 units of time. But then P4 arrives, which has a burst time of 5. So after P2 finishes at time t equals 5, P4 will actually run, and it's going to run. What's the burst time? What's the burst time for P4? 5 units of time. Here we go. It runs and finishes at time t equals 10. But P1 has actually only had 1 unit of time on the CPU. It still needs 7. So P1 finishes at time, sorry, P1 finishes at time t equals 17. And then P2 is the process with the shortest remaining time of 7, or something like that. And then it runs to completion. So a little explanation here. And you can see it's a dynamic system. And in the case where P3 arrives, well, P3 has got a burst time of 9. So P2 um, P I've just got to be careful. P3 arrives. P3 arrives. Well, you can think about it at every stage. No matter what happens, you're going to pick a process, whether it's just arrived or whether it's already on the ready queue. The scheduler, the piece of software that's picking the next process to run, will always choose the next shortest burst time requirement process next. So it'll choose, given any process that's got a shorter next burst time, that process will be picked. And if needs be, the currently running process will be bumped off the CPU. So have a look at this very, very carefully. Look at this explanation in your own time. And I want you to notice that the average wait time for a preemptive shortest job first algorithm is 0 plus 9 plus 15 plus 2 divided by 4, which is 6.5. So check this, please. Just check that. Make sure that's correct. All right. But a non-preemptive uh, shortest job first. In other words, at any given time you're choosing the shortest job to run. But if if another job arrives and it's shorter, you're not going to preempt that. You're not going to boot that currently running process off. And in this scheme, a non-preemptive shortest job first algorithm is going to have a slightly larger average wait time. Can you just check these two claims quite carefully? I think they are correct. Right. So the third algorithm is simply, it's called priority algorithm. And it turns out that shortest job first algorithm is a special case of priority scheduling. In shortest job first scheduling, priority is the inverse of the predicted length of the next CPU burst time. So in other words, if you've got a very short, relatively short next burst time, predicted burst time, um, that process is going to receive high priority. It's going to be executed before processes of lower priority, as defined by predicted length of the next CPU time. So usually we take low numbers to represent high priorities. Let me just check that. Okay. Supposing P1, P2, P3, P4, P5 arrive at time 0 in that order and have burst times of 10, 1, 2, 3, 5. Therefore, you can assign priorities on the basis of the burst times. So the highest priority is going to be B2 because it's only got a burst time of 1. P1 is going to have the lowest priority because it's got a burst time of 10. And priorities can be assigned either externally for some external reason or internally because there's a predicted uh, a predicted uh, on the basis of predicted burst times, next burst times, or priority could be assigned in terms of just well why this particular process is important to run first. I mean, maybe you need you've got two processors, and one is going to release a mechanism to drop a bomb, and the second process is some kind of servo mechanism that's actually going to open a bomb bay door on an aircraft. And obviously, um, the door opening mechanism should be given priority. I mean, for goodness sake, you don't want the bomb to be dropped if the bomb day hasn't already opened, all right? So if you assign priorities on some basis or other, and it might be, uh, as in the case that we've already considered, on the basis of the next burst time, you can actually schedule them preemptively or non-preemptively. And in the case of an incoming process with a higher priority than all the others, the currently running process won't be preempted. It will simply be placed at the top of the queue, right? So if you're looking at non-preemptive priority based, you're not going to kick the one that's running at the moment. You're just going to, when it's maybe finished running, you're just going to move it to the top of the queue. If you've got a high priority processor, you're going to move it to the next position. That's going to be the one that runs next. And um, there is a problem with priority-based scheduling because you can get processors that are effectively starved to death. I mean, because say Chris Kinberg is a very low priority process, um, and there's going to be a stream of new processors coming in, all of which have very low, for example, very low next burst times. I'm not going to get a chance to run uh, the CPU because I'm low priority and um, I need a lot of CPU time, which is ironic. I'm never going to execute or maybe I do, maybe I will become executed, but it'll take forever for me to get a bite of the CPU cherry. So a stream of high priority processes can guarantee that the lowest uh, priority process is always left at the end of the queue. And this is purely anecdotal, but I think it is a fact. At the Massachusetts Institute of Technology, one process on a particular supercomputer was left unattended for 6 years. In other words, it didn't receive any CPU attention for 6 years. I mean, it's it's very sad if that sort of thing can happen as a result of the particular scheduling algorithm you choose. So the fourth scheduling algorithm is round robin, and interestingly, this is used in time sharing schemes. Um, I mean, it's similar to first come, first served, but you add preemption. And the idea here, I mean, this is something that we looked at when in the very, no, I think it was the very early on in the course, we looked at what parallelism was, and we looked at the idea of allocating a queue of processors small amounts of CPU time very quickly in turn, and that action creates the illusion that all those processes, all those programs are running at exactly the same time. Creates the illusion of parallelism. I mean, technically, they're not all running in parallel, but because they're you can't actually say, well, program number 99 is running right now for um, 2 microseconds. It's very difficult to it's very difficult to perceive any kind of break in the um, execution of any one of those programs. I mean, it's as though they're all running at the same time. Video's playing at the same time as audio's playing. So the idea in the case of round robin scheduling is that each process is given a quantum. So I promised at the beginning of this lecture I'd introduce it to a keyword called quantum, otherwise known as a time slice of CPU. It's going to be given a given time on the CPU, a time slice of time. And the ready queue, i.e. the queue of all the processes waiting to run, is going to be organized as a first in, first out circular structure. So the scheduler, i.e. the software that actually picks the next program to run on the CPU, will visit each of the programs and allocate a quantum in turn. I mean, the easy way of doing it is you allocate the same fixed time to each program in the queue. And if a process doesn't actually need all of the quantum that's been allocated, it will voluntarily relinquish control of the processor unit. So what I'm talking about is that if the scheduler has allocated 4 units of time to a program that only actually needs 3 units of time to execute, then after 3 units of time, um, the the process will be voluntarily taken off the CPU, and the next program will be put onto the CPU to run. If it has used, okay, so if it has used its quantum, its execution is preempted. It's preempted. And a context switch is made. So here's another uh, keyword that's very important. a context switch, and that's simply the action of taking a program off the CPU and replacing it as quickly as possible by a second process, right? And if the first process is taken off because it's preempted, because it's used its time slice up, it will be put on the back of the queue to wait its turn again. Using round robin means that the average wait time is lengthy. However, using this way of scheduling it. So, for example, if you have processor 1 with a, a burst time of 24, P2 burst time of 3, P3 burst time of 3, if the quantum is 4 units of time, well, um, P1 will be picked off the queue and starts to run, and it'll run for 4 units of time, and then it's preempted, and it'll be put on the back of the ready queue. And the next process on the queue is P2. It will run, and it leaves the PU voluntarily. I know, in actual fact, it's preempted by the scheduling system. It was given 4 units of time, but it's only used 3. It'll be taken off, and the third process will start to execute it on the CPU. So that leaves the processor unit voluntarily as well. So the average wait time is, well, for P1 it's 0, then P2 is having to wait 4, and then at time 4, let me see, hang on. P1 starts, it uses 4 units of time. At that point, P2's been waiting for 4 units of time, and then it takes 3 units of time to execute. Then P3 has had to wait 4 plus 3 units of time, and it runs for 3 units of time, and then P1 will start again, and it needs 20 units of time. So it'll run for 4 and 4. Okay, so can you calculate the average wait time? 0 plus 4 plus 3 and plus another 4, which I think gives you 17. 4, 5, no, I'm not sure. I'm doing this, I've just seen this change that's been made in the presentation. So it's 0, P2 runs at 4, further 3, that's 7. And then P1 starts again at 10. So I reckon it's 10 divided by, you've got 3 processors, and the average is 10 divided by 3. Can you check that anyway? If there are n processors on the ready queue, and the quantum is little q, units of time, each process gets 1 divided by n of the total CPU time in chunks of q. So you're dividing the CPU time amongst n processors or threads or programs. So each one's going to get 1 divided by n of the CPU time in chunks of q units of time. Each process doesn't have to wait more than n minus 1 times q units of time before it's time to execute it again on the CPU. So think again about that. That's an easy point, easy conclusion, easy corollary to draw. Performance of an algorithm depends on the size. The round robin algorithm depends on the size of the quantum queue. If queue is very large, then what round robin really amounts to is first come, first served without preemption. You choose the first process or thread on the queue, you run it until it finishes, then pick the next. Run that until it finishes, then choose the next. The order of execution is determined by the first come, first served. On the other hand, if queue is very small, round robin in effect is processor sharing. It's or time sharing. It appears, and this is quite an interesting thought, it appears as though each process, so again, there's a little error here, each process has its own processor running at 1 divided by n of the rate of the real processor. So hopefully you can see that, right? Because you're dividing uh, CPU time amongst n processors. Each processor is going to get 1/nth of the total power of the CPU. And logically, it's as though each of the processors has its own virtual processor, a dedicated virtual processor. Right? You need to consider the effect of performing context switches, which, as I said, it's the time taken or it's the action taken from taking a particular process off the CPU and putting another one on. You're swapping them, in other words. You need the quantum to be relatively large with respect to the delay involved in making the context switch. Can you remember that? Can you be able to answer a question on that for assessment in 10 weeks' time or so? All right, just highlighting a possible question there. Turnaround also depends on the size of queue because average turnaround, i.e. the time it takes the program to start all the way to the time it takes to finish, is improved if most processors finish the CPU burst in a single quantum. So hopefully that's sort of fairly of some interest, and maybe you've never ever thought about these matters before, but hopefully there's some of some interest here. Um, Finally, I want to say just a quick word about Java thread scheduling, because at some point in Java, I mean, not yet, I mean, you don't have to worry about Java programming because we're really, in effect, starting Java from the beginning, even though to some of the newcomers, it must look a bit of a nightmare in terms of what we're doing, but it's not. We're going to look at some of the absolute basics of programming and Java programming in particular. We're going to have a look at thread creation because at some point, what I want to be able to do and to show you is how you can actually run what in effect are two programs simultaneously. I mean, maybe one program's actually showing a little video clip on your screen, and another thread is actually uh, performing some completely different activity. It might be showing another video. It might be actually asking you questions to which it's expecting replies through a microphone. So the Java virtual machine, i.e. the mechanism for running Java programs, does actually use preemptive priority-based scheduling. So we've looked at what preemptiveness means, and we've looked at what priority-based scheduling is. And in Java, all threads, all programs, if you like, are given a priority. And the Java virtual machine schedules the runnable thread with the highest priority. So if two or more threads have equal priority, then Java will actually use first come, first serve. And I'm not terribly interested in looking at Java. Um, this is some covers some of the work that we did weeks and weeks and weeks ago, like blocking of a process. But we don't need it at the moment. We don't need to think about it at the moment. And I'm just going to end this duplicate presentation at that point. So hopefully, you know, okay, I've missed something I've just seen. What I did talk about in the presentation is this. Um, so I did actually, and I think I've inadvertently skipped a couple of pages. Because we did actually look at a way of estimating the next burst time on the basis of measuring times it takes a program to execute fully. And it's a recursive definition. Tor sub n plus 1 is a small constant alpha multiplied by Tor n. So that's going to be the nth measurement. And that's added to a very small weighting because it's 1 minus alpha multiplied by the nth measurement. So you're taking into account the previous measurement and you're adding a little bit, little tiny amount more from the last measurement you took. And that's going to become your n plus 1th uh, cycle of estimating a burst time. So I'll just give you that. I mean, to give the idea of burst time a bit of basis in uh, practical timing of programs. Otherwise, the time it takes the program is a bit mysterious. Okay, so I'll finish there, and I expect you to read through all this again and do your absolute best to understand the main features of what I've been saying today. So thank you very much.